total lightning today. There's a new data set that you have available on AWIPS. There have been some implementation issues with that, and we'll go over that and also get you oriented about the data set itself. So a couple of learning objectives today's session. One will be to learn about the total lightning network from Earth Networks, and the other will be to understand a little bit about the total lightning displays and how to start using those and working with those in the convective season. So performance objectives, things you should do after the training session. One would be to begin using the total lightning data for your routine weather watch and thunderstorm detection, observing, and interrogations. When possible, integrate the total lightning with the other existing AWIPS information that you currently use. Also, developing more experience with using the cloud flash data, the in-cloud lightning data, which is usually a precursor to cloud-to-ground lightning. And lastly, to recognize that total lightning flash rate trends can serve as a proxy for thunderstorm updraft intensity. So the data comes in at 1-minute intervals, and so it's more readily integratable with mesosails and radar data and some of the other data that you'll be getting from satellite and other sources. So the significance of the ENTLN implementation is that it's the first national ground-based total lightning network to be implemented in AWIPS. There are smaller regional networks and other total lightning data that some offices have that the hazardous weather test bed has access to, for instance. But this network is actually national, and all of the sites get all of the data. So you'll be getting all the data for the entire CONUS region and a little bit beyond that. It contains detection of cloud flashes, which again will provide a lead time of 10 to 15 minutes over the CG data sets, like the NLDN and the GLD if you've been using those from Visola. It also provides an alternative for thunderstorm cell identification and tracking, and improved situational awareness if you have poor radar coverage areas in your CWA. And let me just go to Pamela in Pueblo. Do you have any particularly poor areas in your CWA for radar coverage?
We sure do. Anything west of the mountains is pretty much not covered well. So.
Oh, wow. West of the mountains.
Well,
okay.
San Luis Valley and all of our western mountains, we don't get a whole lot of good radar coverage, so, yeah.
Right. Well, you probably know Steve Hodanish, who is a lightning enthusiast.
Yes.
And he was quite excited over the winter season at the ability of the total lightning network to pick up on the snow squalls and heavier snow showers.
Uh-huh.
So that's another advantage of combining the total lightning data with the other data sources like satellite and others.
Yeah.
So I know you guys are starting to look at that and have been and looking at the not only the winter applications but obviously the summer ones as well.
Yeah, definitely.
Okay, very good. So here's a look at the network itself. It's composed of ground-based stations, so that's what all those yellow dots are. And you can see there's some in southern Canada. There's a whole bunch in the Northeast Corridor region. There's a big bunch in Florida and a big bunch in Texas. And then elsewhere, it's sort of irregularly spaced. So that kind of gives you a sense for where the stations are, and if there were to be a big event, for instance, a hurricane landfall or something, that's when the number 24 hours, we've learned that they may have changed the coverage domain, but this is what we're expecting it to be when things are back to normal, so to speak. And you can see it does go out well over the coastal waters and south of the border, so to speak, and even north of the border. So you should be able to see things coming your way if you're in a coastal area, or if you're in a border location where we wouldn't have radar data, for instance. So when we talk about lightning networks, one thing that gets one metric is the detection efficiency. And so we have two figures here, one on the left for the cloud-to-ground lightning data from the Earth network. And you can see that in the deep red there, it's pretty much 95% over most of the central and eastern U.S. and much of the west. And then it kind of tails off somewhat due to terrain and station spacing and availability. So it is a little more challenging in the west, but I think you'll be surprised at how good it is as well. So in terms of the total lightning, which would be the cloud-to-ground strokes as well as the in-cloud lightning flash activity, that's what's shown on the right. And you can see that the detection efficiency is somewhat less for that, more in the 70 to 80% range across the U.S. Again, where those clusters of ground stations are denser, you can see that there's a little bit higher rating for the detection efficiency in that orange color. The other question, or the other metric that's important for the lightning network and lightning data, is the location accuracy. So the CG location accuracy, which is something that we're most concerned with for public safety and other applications, is shown here. And you can see that in some of the densest station areas that it's less than half a kilometer, but generally across the CONUS, location accuracy is within 1 kilometer. So it compares reasonably well with the National Lightning Detection Network, but if you were going to go for the absolute, closest or smallest error, NLDN still seems to be the best. But in practice, folks are using both networks and together to get the best sense of what the activity is like. So we had to come up with some usable, workable total lightning definitions. Lightning definitions can get out of control in a hurry, so we've boiled it down to cloud flashes, the in-cloud lightning activity, and cloud-to-ground, which is similar to the NLDN data that you've been using for years. So the idea is that the CGs are what you're used to seeing, and the total lightning quantity is combining the CGs with the in-cloud data to produce the total lightning quantity. So getting down to a particular description of what the network actually senses and detects, this conceptual model was put together by Dr. Rulowski at NOAA. And what it shows is the lightning origin at point A. This is a lightning strike over the DC area. So originating at point A, and then you'll see there's some lines and dots, and that's the high-resolution lightning mapping array in the Washington, D.C. area that detected this same singular flash. So that shows a trace that goes down to point B, where the strike struck the ground. And at point B, there's both an Earth Networks cloud-to-ground flash and an Earth Networks cloud-to-ground Earth network pulses. So a pulse is simply an electrical discharge along the lightning channel that Earth networks can sense. So you see there's not as many points and as many locations as the high-resolution lightning mapping array where the lines are. But you still have a much greater number of detections of pulses than you do for the cloud flash or the in-cloud pulse, or the in-cloud flash, the CG flash. So one use of that information is to define the volume of the entire lightning strike or stroke. So if you look at this picture, we tend to just plot like pluses and minuses for CG strikes, when in reality it takes up a volume, and that volume can be on the scale of tens of miles or even larger than that. So the pulses are an estimate of what the aerial coverage is of the entire lightning activity for that lightning strike. So in terms of AWIPS, these are the terms that you'll see in the product legend when you load the data. You'll see that we specifically call out Earth ENTLN cloud-to-ground lightning, which is in fact the cloud-to-ground strikes, similar to what you get with NLDN. And the cloud flash data is the in-cloud data, all of the in-cloud flashes that we talked about and just looked at. And then the pulses are the fundamental component of the lightning data set. The pulses are grouped by Earth networks into cloud flashes. So you have the most detections are pulses, and then those get grouped into a smaller number of flashes, cloud flashes, and they also calculate the CGs. So in AWIPS, your menu system looks something like this, where you have the ENI total lightning, and then you have both a plot menu and a grid menu. Here's an example just showing a 4-panel, and for people just getting used to the Earth Networks data or network, this is a good way to start out, is to compare the Earth Networks data with the NLDN or other lightning data that you may have access to. So you can see that on the left we have the NLDN plot of the CGs, and then in the lower left we have the Earth Networks cloud-to-ground lightning plot as well. And then in the upper right, this is some of the new information, is the Earth Networks cloud flash data. So these are the data that would most likely precede and be coincident with the CG data. And then in the lower right, for comparison, is the Earth Networks pulse data set, which provides more numerous detections and is a good way to look at the aerial extent of any electrical activity in the column, in the vertical. So the other part of the implementation is lightning grids. And so under the ENI total lightning grid menu, you'll see that there are a bunch of resolutions there, and then some different default timescales ranging from an hour down to 5 minutes. So here's a little closer look at that. You can see that you have broken out, you can specify the cloud-to-ground density if you're just interested in which flashes are touching ground. You can also look at what's just the in-cloud activity, and then the total flash density, which is both the in-cloud and cloud-to-ground. And then the pulse density is also there as well. So in terms of the grids, you'll hear terminology like flash density and other ways of gridding lightning data. In AWIPS, basically basically what happens is when you create when you select the menu option for a lightning grid, it takes the point data and grids those up on the fly over the domain that you have displayed and produces the grid on the fly. So one bit of caution here is to make sure that your area and time or number of frames is reasonable to do that, and that changes, of course, with the amount of lightning activity and number of points that the software would have to process. The other thing is, shown here is we have 5-kilometer grid boxes, 20-kilometer grid boxes, and 40-kilometer grid boxes. So if you create a grid, say, at 5 kilometers, and then zoom into that grid, the grid spacing doesn't change. It maintains the 5-kilometer grid spacing. So there isn't what's called progressive disclosure with the AWIPS lightning grids, and that applies to the NLDN data as well. So here's a quick example. This is over Louisiana, showing the ENTLN flash rates. There was a warning issued, and subsequently the severe weather report of large hail. So just a quick example to show you what kind of display is possible just using the lightning data alone. Obviously, you'd want to combine it with radar and other data sources as well. Here's another quick example just showing a set of storms, and you can see that the lightning flash rates increase quickly in the storm in the middle there, and 1 3/4 hail report follows shortly after. So one of the considerations that you'll need to make when you start using it at the storm scale is the legend at the top, the number of the flash rate display. You may want to localize that to your area if your storms have smaller or larger flash rates. You'll want to adjust that so that you get a good range of detections. Here's an example of combining the Earth Network's total lightning data with some of the MRMS products, this particular one being the mesh, the maximum expected hail size. And you can see where the mesh kind of peaks out in values. It corresponds pretty nicely with the storm reports and also the higher flash rate cores as shown in the lightning data. So if you do have a big event, you might want to go back and review, how the total lightning did in terms of being a predictor or being a precursor for situation awareness cues. So in terms of the AWIPS implementation, the reason the teletraining is being offered is there's a patch which should fix some amount of the problems we've been having with the data ingest. So one issue is that there have been data dropouts over the last, year or so, and they were caused by different reasons. We finally isolated it down to an AWIPS data message parser bug, which is basically a text bulletin comes in, it gets decoded and parsed, and then that data is the point data for the lightning. And there was a bug in there which was causing the data message to be rejected by AWIPS completely. So I'll show you what that looks like in just a minute. There's another issue that occurs, and when you load a sequence of frames, say a 15-minute data sequence or image sequence, the last frame in the loop is not complete in terms of the 15 minutes. That gets fixed in 16:2:1, and when it is fixed, then you'll get, for instance, 1 minute, a 1 1-minute sequence would have all the data, 5-minute would have all the data. So that's a change that's coming, but you won't see that immediately. So in terms of the lightning data outages, the message parser bug affected both the Earth networks and the NLDN data. And so it affected all your AWIPS and thin client and other ways that you view data with AWIPS. There were more outages with the Earth networks data than with NLDN. And obviously that could impact warning decisions. We're still seeing probably 4 to 5 1-minute data outages per day. And so if you're really unlucky, that 1-minute outage could occur in the middle of your monitoring a storm or warning on a storm. So there is a fix that's becoming available next week to all 16.1.2 sites. It won't fix all the outages, but it'll make your Earth networks data much better. Here's an example back from March 8 of showing what a data outage looks like, and this is on a northern hemisphere scale. So you see there's a ton of lightning activity, and then where the red arrow is, you can see that there's a data dropout there, all that white space. And so that occurred at 10:57, and then the minute following that, when the data comes back, is not a complete minute of data. So there's what we're calling and referring to as a partial data outage, where the blue arrow is in that minute. So here's a little bit closer look at that, a little bit different example, but you see what happens is that you're going along fine, you have data, then all of a sudden, for 1 minute there's no data, and then in the minute following that you get some data, but not all the data. So how would that look like if you were monitoring a storm? Here's an example, again from March 8. So you're at 13:08, you've got a nice lightning flash rate core there, you're tracking that into 09, and then the data outage occurs. So at 13:10, AWIPS would not produce an image for you because it essentially has no data. So you'll see in the next example here, you'll see in the legend it actually says no data loaded. So and then at 13:11, the next minute, that's when the data comes back, but it's not the complete minute of data. So you see what we're calling the partial accumulation there. And then it kind of resumes at 13:12. So if you went from 13:09 to 13:12, you probably wouldn't make much in the way of a dramatic warning decision, but it may sway you in the wrong direction if you compared 13:09 to 13:11. Okay, so here's a little bit of a walkthrough of what this looks like if you got it all plotted in minute by minute in AWIPS. So if your data dropout occurs at 15:18, and then your partial accumulation is the next minute at 15:19, you can see in the data legend down below at 15:18 it simply says lightning plot not loaded. So that's basically your main indication that you've lost it for that 1 minute. And then it gets a little bit trickier if you're working with the grids at longer time scales. The 1 minute grid, it would show up, you would just see everything go black, but at 5 minutes and larger accumulations of time, it would be harder to discern that, and again may sway you in the wrong direction. So best practices in terms of dealing with these lightning data outages: be wary of unrealistic decreases in lightning, and always confirm the data using 1 minute plots and sequences that you'll have available, you should have available now. And also monitor for outages when using total lightning as part of a significant warning decision. So, let me pause there. Are there any questions about the data outages? We'll ask the Buffalo group since you've got a bunch of folks there.
there are no questions here yet.
Okay, very good. All right, so Matt Elliott at Sterling put together some bundles to help with displaying some of the lightning data in AWIPS. So we'll take a quick look through some of those and kind of give you some examples for how the data could be used for different applications. So one of the applications is lightning extent. It's simply is there lightning activity or not? You might find that important for your tasks or aviation or outdoor venues, that sort of thing. So this display here on the top is showing you the ENTLN pulse data. So there's 85, 88 pulses being detected over that area. And you can see that as point data, it's really not all that helpful because, you have denser areas and less dense areas, but how you would actually make quantitative use of that remains to be seen. So, but what you could do is create a grid and kind of show the lightning extent in terms of just a mask of where is there total lightning activity versus where there isn't. And that would help to convey to your decision makers, where is current in-cloud or total lightning being detected and where it isn't. So here's a little bit more showing the Cape Canaveral area, obviously a place where lightning sensitivity is pretty strong. They do lots of space stuff there and launching rockets and previously the shuttle and other things, so they're pretty lightning sensitive down there. And so you can see, again, with the four-panel approach, the NLDN in the lower right, the ENTLN in the upper right, you can see that those two compare pretty favorably and show pretty much the same picture. On the left is the new information. So the upper left is the Earth Network's Cloud Flash data. You can see that it covers a little bit more area and is also a little more continuous because you're getting the total lightning versus just the CGs. And then in the lower right, as we just talked about, the pulse data, which is more numerous and does a better, more continuous job of showing the regions where any lightning or even just cloud electricity would be located. So it's maybe a little bit of an overestimate, but if you're looking to be more on the safe side than on a conservative estimate, then that's one field to look at. So here's an example of a bundle that Matt put together to show every minute for the last 30 minutes, and then color code those. There are some sequences available in AWIPS for short time ranges, but this obviously gives you a little bit longer time frame and allows you to track individual storms with the lightning data as well. So we have a site where those bundles are available, and I'll provide those in a follow-up email. Here's another example showing the Earth Networks and NLDN data on the right. You can see, again, mostly similar depiction of the lightning activity. And the new data on the left, the cloud flash data at 1 kilometer in a gridded form, and the Earth Network's pulse data below that in the lower left. So you can see it gives you a slightly different sense over these 12 hours of how much lightning activity or electrical activity there was, particularly in cloud with the cloud flashes and with the cloud pulses. Here's another example from along the Gulf Coast showing, again, 12 hours of lightning data in both the total cloud flash, the cloud-to-ground flash, and the pulses. And you can see the pulses provide a little bit more of a continuous depiction, and Matt has annotated on there where flash floods and large hail occurred during that storm sequence. Here's another example showing the Earth networks, again, divided up from the total flashes to the cloud flash data, and then the cloud-to-ground flash as you go around clockwise. So the pulse data is also shown there, and you can see the tornado and storm reports overlaid on that. Moving on, here's another example showing some more of the MRMS data. So the cloud flash data in the upper left with the storm report, the large hail reports, matching up nicely with the mesh data from MRMS and also the rotational tracks, both low and high, as shown there. Here's another example showing, again, the correspondence with the cloud flash data, which should give you a little more lead time than the CG data. Some words of caution, some of these bundles or displays that I've just showed you, the bundles tend to use lots of memory, so recommendation is to not use them on the WarnGen computer. Best to have that on a different workstation or have someone else working those. And then also using smaller domains versus larger domains and shorter time sequences to the extent that that's possible. Especially if you're looking at 1 minute data, it's hard to get too short with your time sequences. So we've created a quick guide. You may be familiar with some of these for other data sets. Scott Rodlowski sort of led the charge on this one with contributions from others, including the hazardous weather testbed folks. And so on the first page, we basically just go through the basics, the terminology, and what you can see in AWIPS in terms of the different plots and grids. And then on the back, a reminder of the conceptual model and what the total lightning data shows you versus what the NLDN has been showing you for years. And you can see the detection efficiency and shown there for reference. The ENTLN data is also available via archive, so if you have an event that you want to go back and look at, there's a client that Earth Networks provides to the Weather Service called Streamer RT. It's a web-based browser client access to the Earth Networks data service. So if you have IMETs or others that get deployed off-site and they want to have a way to access this data, there is a way to do that. Contact your local SSDs and they can provide you with the information on how to get accounts for that. I can also do that if you need to try a second source. There's also data available for older than 6 months. 6 months is online. Older than 6 months, we can also request that from Earth Networks through your SSD. Again, a reminder of the performance objectives. The idea is to start integrating the total lightning data with your weather watch and storm interrogation procedures. And for more info, I'm Brian at FDTD. We're also working with Mike Magsig and the WDTD folks down in Norman. There's also an NWS Virtual Lab Lightning community. There's a blog there, and we'll be sharing files and examples and the quick guide there as well. There's also a lightning working group that meets every Friday, and if you want more information then contact me for that. And your regional SSDs, they can be helpful with AWIPS 2 issues and sorting out anything in terms of the Earth Networks accounts. One last thing, social media usage guidelines. Basically, the only restriction on posting either current, past data from Earth Networks is that you not set up a procedure or automated script that would post the lightning imagery frequently to the website automatically, say once a minute or once every 5 minutes. You are able to post any of the imagery, the grids, the plots, etc., on social media, and the only request that Earth Networks has is that you do quote the source the way that they've outlined it there, Earth Networks Total Lightning Network, ENTLN. So they also offer the data on their app free of charge, so people wanting access to it can get it on their smartphone app as well. So here are some acknowledgements, lots of contributors to this training, and at this point I'll close and take any questions. Let me go office by office. We'll start with Pueblo, since you guys are lightning enthusiasts down there.
I don't think I have any questions, but thank you.
All right, very good. How about Charleston?
Yeah, hi, this is Steve at Charleston. I've got a really basic Lightning 101 type question. How did you smooth that gridded data? What did you use in AWIPS to smooth that?
Okay, good question. If you create your grid, or if you select the grid menu item, you can go into the where it says color table adjustment.
Yep.
And where you'll see it, there'll be a checkbox to interpolate, and it will interpolate that blocky sort of gridded depiction into the smoother ones that I showed in the presentation.
Outstanding. All right. My other question is, you were talking a lot about the 1 kilometer, the smaller, finer resolution grid spacing. Why are there 20 kilometer grids available in AWIPS? What would be the function of that? We've been struggling with that a little bit here.
Right. Good question. The original requirements for the implementation included the NCEP centers. So folks like Aviation Weather Center and Storm Prediction Center, they tend to look at the whole CONUS and look at larger scale grids. So those requirements were partially based on input from the national centers.
All right. Yeah, we're on a WFO perspective, so that's a great way of looking at it. Thanks a lot. It's a great webinar. Thank you.
Okay,
yeah,
great.
I have a question too from Charleston.
Go ahead, Mike.
I noticed that we only had really like one sensor anywhere near us, and you talked about the potential for those to go out, during a hurricane landfall or something like that. Is there any plans to add more in our area? Because we kind of be in a little bit of a hole here compared to Florida and then the Mid-Atlantic up to the Northeast.
Right. Well, yeah, there's good news and bad news. So the good news is that unlike radars, the actual site location of the detector, its geography in relation to where you're located is not as critical as it would be for like a radar. So being in Charleston, you actually benefit from the Florida and Northeast corridor, that huge cluster of sensors in both of those places. That actually provides better detection for you in the Charleston area. So.
Okay, I just noticed on a few of those where you had shown something about accuracy or things like that, there always seemed to be a little bit of a weakness over us, and that just was a little concerning.
For the location accuracy?
Yeah, like, right there, that map, and then the previous map, there's kind of a little bit of a weakness over our area.
Okay, yeah. I mean, I'd be interested in your, if you're able to actually notice that in the data. Let us know, and we keep in touch with Earth Networks on a regular basis, and they certainly want to improve the network everywhere. So, if you find that that's an issue, let us know, and we'll pass that feedback along.
Okay, my main question was just to know if there's any more coming, so it doesn't sound like there is at this time.
Well, the part of their business model is that they work with the local school districts and the sports leagues. They have a relationship with the NFL and Major League Baseball and a lot of other customer base that they have. So they do try to make sure they have optimal coverage across the CONUS for their main customer base's protection of life and property. So they're in the same business we are, but they have a little bit different bent on it. We're trying to do more with the storm morphology and severe weather prediction and that end of it, whereas they're simply trying to detect any lightning and then provide that notification to their local users.
Okay, sounds good. Thank you.
Sure.